Okay, so I'd like to welcome everyone to the 958th monthly meeting of ATMoB. Our guest speaker tonight will be Dr. Gabor Furesz. We'll be talking about LLAMAS, 2,400 little eyes for one big telescope. Very, very interesting talk for a very interesting instrument. And our agenda is the typical agenda. For the President's welcome, I'd just like to say welcome everyone. The holidays coming up, so I hope we all have to spend time with family, enjoy all the holidays, also enjoy the winter objects that come and bundle up out there because it's cold. But hopefully we have some nice clear skies upcoming. Next, we have Glenn and Rich with the observing report.
Glenn's here somewhere. Here's Glenn. Glenn's
Right
here.
here.
He is.
We're going to sit down and have you handle the whole thing.
Side to side, but it's a space cadet.
Okay. Well, this is there's also a Far Side cartoon, same thing. Every time I see it posted on Facebook, I just burst out laughing because I don't know why I find it so stupidly silly, but that's pretty funny stuff. Anyway, yes, the inventor of the practical joke. And then the quote of the month is one of my favorites, is that astronomy waits for no one. I was in Merrimack, New Hampshire last night, sitting right on the grays line, the southern grays line of that occultation of Mars. And I had some beautiful, beautiful views of clouds. And I actually watched, just so I would know when to pack up, I watched the event transpire on Sky Safari Pro, just running in real time. And it was glorious. It was glorious. But I was confounded by clouds, as we are like 65% of the time in New England. So, you know, that the grays happened, it came, it went, and I just a sad story to tell about it. But that's one of my favorite things in astronomy. It waits for no one. If you've got something you want to look at, get out there and have a look at it.
I'm going to jump in on that. That's where it's good to have a second hobby. I'm also, as you know, an avid angler, and cloudy weather is great for fishing. So I was out in the pond yesterday having a time. Fish were biting like crazy. So yeah, I hated to miss the occultation, but I still got my fresh air.
There you go. I do all my fishing up at Stop and Shop, of course. But, you know, here, go ahead and talk about these.
Oh, all right. Let me get my glasses.
Some Mars images.
Yeah, we had some images. Now, there were tons of them taken last night, but we didn't have time to, there wasn't time to put them on the slide deck. But of course, Mars is in opposition as we speak. And club members have been sharing some of their images. This is one taken by Sal Larisha. And I don't know if Sal, I think he put on the website there what he used. But I know this is with a 6-inch scope, so that's pretty impressive. The only thing I recognize, I think this is called the Sidus Meridiani. It's one of the features. And I think Certus Major is probably over here. They're already set. But that's a nice shot with a 6-inch scope. We'll go to the next one.
Those polar clouds around the North Polar region of Mars have seemed to have diminished a little bit. I've been watching Mars for about a month now, and they were prominent back in October and November, but they seem to be diminished now. Mars is currently close to Earth, so I'd encourage you to get out and use the highest magnification your aperture will hold and the atmosphere will hold, and be patient. Those features are pretty subtle to see. But here's another nice shot. Look at that.
Again, it's amazing. Those of us old timers remember what pictures were like in our textbooks back in the 1960s. And the major observatory couldn't come up with something like this. So it's a test to the modern technology and some of the imagery we have. This was from Nazir, I think.
Nasmith, yeah. And here's one. This unfortunate is Doug. You're here tonight,
Yes,
right?
I'm here.
But we can't get your.
I might be able to.
I could get the animation to run on my computer,
Yeah,
but
this is kind of neat.
when it crossed over, it didn't come with the picture. These are
You have shared it though. How many saw his images that you sent to the ATMoB website or to our email? Was it working there? Oh, there we go. That's something.
Mars can be a little frustrating to watch. If you're looking for a particular surface feature. Of course, Mars rotates on its axis every 24 hours and 37 minutes. Unlike Jupiter, where the red spot comes, travels across the disk, and goes away in a matter of a few hours. You sort of have to wait it out with Mars. And when you look at different observers from around the world, on a given night, they're showing you different parts of Mars because of the time difference between the two observing sites. You have to wait about 36 days that 37 minutes a day for Mars to sort of catch back up to you at, say, 8 o'clock in the evening. So you just have to be patient watching Mars. I like to use, I have a Bader semi-apo filter that I use, and it seems to enhance the subtle features a little bit, but they're very subtle. You have to be super patient with Mars. But we only get this opportunity every 2 years and 2 months. And this is probably the last of the close oppositions. You know, Mars orbits the sun in an elliptical orbit. So there are times when we're particularly close to Mars, every 15 to 17 years. So we've come away from that period. We're about to enter the 2 years and 2 months where we're particularly far away. But 2033-ish, I think we'll be back in a pretty good place. But
I don't know if I'll be back in a good place.
remember, astronomy waits for no one. This apparition will come and go. Okay, so think about 2033. And so here are the observing highlights for the month. Now, there wasn't much going on, but I put some things down. Glenn loves variable stars, so on Monday, December 12th at 9:38 p.m. Eastern Time, Algol reaches a minimum. So that's kind of a fun star to watch because the eclipses don't last all that long. And if you go out there at the minimum at 9:38, over the next few hours, you can watch it reach its maximum brightness.
Yeah, this is when you could start, say, 7-ish, right after supper.
Yep.
And if you're looking for charts and things, you can go online, just Google Algol. They have the comparison chart, so you can identify the different stars and you can make comparisons. And just check it out every 15, 20 minutes. You make your own data sheet. And after a couple hours, I'd say probably if you observe that until just a little bit before midnight, you'll probably get the whole return as well. It drops from about, I think it's 2.4, something like that, down to 3.2, 3.5, and then back up again.
It's pretty noticeable.
Yeah, oh, definitely.
It's real noticeable.
Another thing you might want to do is go out at 7, take a look at it, see how bright it is, and then just watch whatever you want on TV, come back out again right around the time of max and just see how much it's dropped. You know, full magnitude and a half in just a couple hours. So it's a fascinating stat to look at.
Yeah,
it's naked eye.
It's been known since antiquity. People have been observing this for like a long time. Anyway, on December 14th, the Gemini meteor shower peaks, but the moon will be very, very bright. On December 21st, where we hit the winter solstice, Mercury's also greatest elongation east at 20 degrees from the sun. Very challenging. The ecliptic runs very low to the southwest horizon at this time of year after sunset. And so it's a challenging thing to look for. Of course, I would suggest you go look for it in the daytime, but that's also, it's got its own challenges. But if you want to try and find Mercury in the daytime on the 28th, Venus and Mercury are about 1.5 degrees apart. Venus is on the far side of the sun, but it's still minus 3.9 magnitude. And now it's actually pretty far away from the sun, well, 20 degrees. And so mid-month in January, about 20 degrees. That's a piece of cake to find it in the daytime sky. It's bright and it's far from the sun. So you don't have to worry too much about that. And then the very brief quadranted meteor shower peak is on January 3rd, but I haven't got my handbook yet, so I couldn't figure out when it peaks. But
it's very, very short, very short.
Yeah, a couple of hours. So things have to work out just right. And then because there wasn't much to look at.
Kelly wants to say something. I just want to mention, if you're successful in seeing Mercury and Venus right at the end of the month, you have a chance to see all 5 naked eye planets at once.
Well, there you go. Perfect. That's good stuff. They were counting them off at one of our star parties because we looked at Saturn, Neptune, Jupiter, Uranus, Mars, and then somebody said, "Oh, and here's Earth," right? So we covered a lot of bases that night. It was pretty fun. But here we go. Earth reaches perihelion on the 4th. There's the Mercury elongation. Venus is 20 degrees east of the sun at mid-month. Saturn is setting early these days, so you got to get out there and look at that. Neptune is setting at 9:30 p.m. and Jupiter's gone by 10:30 p.m. This is all mid-month January. So Uranus is up and available, and so Mars transit is about 8:30. By mid-month January, look at the apparent disk of Mars. It's down to 12.6 arc seconds. So that's largely due to the fact that the Earth is pulling away from it. And so now is the time to get out there and actually observe that. Now you said you had some asteroid occultation things to talk about, right?
Okay, Bruce Berger got me into this, and I haven't. There was a really highly publicized asteroid occultation where the star Regulus was eclipsed by, and I can't remember the name of the asteroid, but that path went right up the east coast. So we would have looked at Leo the Lion and Regulus would have disappeared for a couple of seconds. It would have been an amazing thing to see. The entire East Coast was clouded up. So none of us, I guess, got to see it. but you rode
No
the
one
airplane.
actually observed that event. It was
And that's
cloudy
rare.
all the way along the path.
I think the next one is probably, I think Antares is going to be eclipsed from places in Europe, and that's probably the next decade or so. Yeah, they're actually more common, but again, for one particular place on Earth. This is asteroidoccultation.com, and I check it out every month. It has them for the whole world, but I look down the column of where these are going to happen. There were two that came about, and I'm going to just step out front here for just a second so I can see this a little better. This is one called Gerlinda. And this asteroid, the path is going right from Alaska, right across the United States. And what it's going to do, it's going to hit probably the northeast part of Massachusetts, right in here. So I would say if you're in the Chelmsford area, you probably have a shot at this thing. If you're at the center of this line, you have a 99% chance that something will happen. These are always kind of iffy. But I thought it'd be an interesting one. By the way, you know how Mario, I had to throw this in, Mario Marder's been so good at these eclipse expeditions? Well, he set up one for this particular event. And he found this isn't the best site. He picked a site up here in the Northwest Territories on the shores of the Great Slave Lake. It's a nice wide open area. And
Just tell them.
yeah. And the accommodations, well, it's actually an igloo, but it'd be worth a shot. Anyway, this one,
Does the eagle rotate like with a like a dome?
you know, I didn't think of that, probably. Okay, anyway, the maximum lasts about 8.6 seconds. And it'll be right just to the south of one of the stars in the Great Square of Pegasus. So if you're really interested, it's kind of, I guess if you call it an advanced observer type thing. But I would definitely encourage you to try. Just go to that website and look it up and, look it for yourself. The time isn't too bad. I've got down, for as far as an Eastern time, what did I put down? Oh, yeah, there it is up there, 8:48. So it's kind of a convenient time. And yeah.
I was going to say, a 12 magnitude star, easily accessible in an 8-inch telescope or larger. 15th magnitude asteroid, not so. So the idea is to do your homework to prepare for this. If you really want to see this, go. We can send you the catalog number for the star, so you can use some software, like Sky Safari Pro, for example, to go and track that star down a night or two beforehand, so you know the star field. And then watch that star, 12.3 magnitude. You'll never see the 15.3 magnitude asteroid unless you've got a big honking telescope. So what will happen is all of a sudden that star will wink out, and then it will wink back on again. And like Glenn said, this path isn't etched in stone. There's always some error bars. As a matter of fact, making measurements along this path will help to refine that path, because what it really does is help to refine.
Another thing you can do is
Find the orbit of the asteroid.
if the observers line up perpendicular to the path, you can actually get the shape of the asteroid itself.
Yeah, pretty cool.
Takes a lot of time here, but that one anyway, I guess Kelly's going to invite us to his house. We'll have a little star party there in Chelmsford.
So somewhere between 8:48 and 8:49.
Yeah.
If you get to 8:50, time to go in.
Time to go in.
Here's another one.
This one is, what's the name? Corolla. And this one's going basically straight across the United States. And as far as Massachusetts, it goes right across basically the Mass, New Hampshire, Vermont border. And I think the clubhouse would probably be right in the center line. So this might be a good project for one of our telescopes there to get the observations when it drops out. It's going to go from, the star itself is 11.5, the asteroid is 15.7. So you're seeing a 4-point drop. It's not quite as long as the other one. This will be a couple of seconds, maybe 3 or 4 seconds in length.
Not bad,
And
right?
the stars here, this one, if I wrote it down here, it's going to be about 10, it's an area 10 degrees south of Pollux, so it's in the Gemini area. So this is the middle of the night one. It's actually the early morning, so it's a little on the late side, but worth it if we get to see something.
Yeah, be fun.
It's worth a shot.
Yeah. All right, so here's the Observers Challenge. Roger Ivester and Sue French's Observers Challenge for this month is Iota Cas. It's about a 4.6 magnitude star in the sky, but it's and it's easy to find right off of Cassiopeia, and this is a high-resolution image of the whole system.
Yeah, this was adaptive optics by the Lick Observatory, and I just want to put in the scale. You've got the 3 main ones: the A star, which is about 4.5 magnitude; B, as I recall, it's about 7th magnitude, and C down here is about 9th magnitude, and the adaptive objects show that C is a very close binary pair. This is about a half arc second here. Same up there for A, just very close together. And I just put, again, an image of Uranus to get an idea. There's a whole planet Uranus. You think how small the disk of that is, and that's still bigger than the separation between these two stars. But I've separated them with a 4-inch telescope, so that it's very resolvable. The problem is the difference in brightness. If they were equal brightness, it'd be fairly easy. But again, you're talking about 4.5 down to 7 here. So this star tends to outshine that one. You need some pretty steady seeing to pick this up. But it's a nice triple star. It's a pretty sight. And it's easy to find again.
Like I mentioned in my 19 plus objects, the challenge really is to be able to separate the A and B pair. You know, what's the smallest aperture telescope you can do that with?
Yeah.
You can always stop down your instrument. You know, just make a simple cardboard mask and in incremental stop downs and see where does B drop off. And also note the colors. In my 20-inch, C looks distinctly orange.
Yeah.
So it's a very pretty star system.
It's a K-type star. So that wasn't just his, just an illusion. It actually is
Delusions,
that
yeah.
color.
No.
And in fact, this star, I think, is also K or an M. That one is a white star. It's an A-type star. This one is a mid-F, so maybe a little off-white. But again, when you have stars like this, there's always this contrast. It makes it kind of hard sometimes to figure out the exact color.
Yeah.
But it's a pretty triple. The wide pair, even that, you're talking 4.5 magnitude and 9th, and a little under 7 arc seconds. That can be kind of tough. I split it with a 3-inch scope many years ago, but you want some good steady seeing.
Yeah.
Okay, we might as well go to the
Fine.
others. I didn't have a lot of submissions. This is kind of hard, but Doug Paul took this picture. He parts of the diffraction rings, and North is up in this, and I made a sketch. I forget. I think this was with a 4-inch scope. Oh, it was 6-inch. 6-inch reflector. There's a triple there. The orientation is the same as in Doug's picture, and there's a triple. And this star out here, that's about 2.5 arc minutes away. It's the Washington Double Star catalog includes that as one of the a part of this system. I don't know why, because it's a long way out. But it's a pretty sight, and even in low power, these are 8th magnitude stars. It's a nice group of 3 stars together, but it's a pretty sight. Again, very easy to find, easy in a 6-inch telescope. But I'd like to see if somebody could pick this thing out. I'm going to try for a 4-inch scope, or maybe even a 3-inch refractor, see if I can split it if the seeing is good. And thanks again to Doug, by the way. That's a
great shot.
And you're there. Do you want to give us some particulars?
That's done with a 5.9-inch instrument, and 88,000 frames, saved only 1% lucky imaging. And that little tick mark under the main star that's where 2 diffraction rings cross, one from the main star and the other from the B star.
Cool.
I have another image of that, which I'll post on the forum, where I have up to five airy disk rings.
Oh, nice.
From you do a little bit of stretching on that image, and it brings those artifacts up.
And remember, Uranus is the size of my hand. That is something else.
If you haven't tried double stars in a while, do go out and observe them. They are kind of fun, especially if the moon is bright. There are dozens of beautiful double stars with varying color contrasts, and so they can be a lot of fun to look at. If you use a refractor, especially a refractor, with high powers, you can see the airy disk and the diffraction rings, and it's just very pretty. I particularly enjoy the airy disk in the refractors, small aperture, big airy disk. But like a star like Antares, the color in the airy disk is just so perfectly pure that it makes it absolutely beautiful to look at these stars with refractors. Or just stop down your reflector, make an off-axis mask that misses the veins for the secondary, and then it's refractor-like in its abilities. So yeah, get out there and check these guys out. And this is the one for
Preview for next month. Yeah, NGC 1245. It's an open cluster in Perseus, midway between Alpha and Kappa, and it's about an 8.5 magnitude object. This one I haven't seen yet, so I'm gonna play with this one with a little 3-inch reflector I've been using for years, my little Edmund reflector. It should be visible. According to the literature I've read, it's visible in binoculars as a fuzzy patch. And in one of the handbooks I saw, there was a description of it with a 4-inch telescope, and it was still hazy. The brightest star is about 12th magnitude, so you're going to start to resolve things with a 6-inch scope. It'd be really interesting, a 25-inch scope from ATMoB to see what that would look like.
Yeah.
But it's a large cluster, about, well, not large, it's about 10 arc minutes across, but it's about 100 stars up to about 12th magnitude. You can see in that picture, it's very rich.
And you recognize the sort of wishbone shape of Perseus here. Here's Algol right here. And at minimum, Algol and Rho are about the same brightness. The other thing, so what to look for in this constellation, Eta Persei up top there, is a pretty double star also. It's a really nice double star.
And I think this one right here, that's a Struve double too. That's a pretty
That
good
little guy?
Struve 331, yeah. They're everywhere.
Glenn's always got me looking for Struve doubles. And I think that's it.
Yeah, Doug Paul, by the way, just want to give credit. Doug took that picture over there,
nice.
so we nice little preview there.
Nice job.
I did read where there was a triangle of stars that were 8th magnitude, 9th magnitude surrounded, but that just looks, that's going to be an interesting object to check
Yeah,
out.
check that out.
And
Add
I
to
think
your,
that's it.
add it to your observing list. I think that's it for the month.
Keep looking up, stay healthy, and have a nice holiday, by the way.
Question, Bruce.
Just a sad note, I believe that the earliest sunset was today.
Uh-huh.
So the sun is going to start.
Why is that a sad note? This is a glorious night.
No, it's a glorious night for tonight, but it means, from an astronomy point of view, it's going to be light later.
Yep.
You know, when you notice that, again, if you're a variable star observer, because one of the ones I was looking at years ago is Eta Aquila. It's a, I gotta stop and think, not Ara Lyra, a Delta Cephei type star. And I was looking at that as soon as it got dark enough to see it, because it's a naked eye star. And boy, it didn't take long. Hey, I was looking at this the other night. Now everything's getting harder and harder to see. You really notice these things if you're out right, if you want to get out as early as you can, you see right away, a couple of minutes from the time I was out last time. So yeah, the nights are going to start getting, the sunsets are going to start happening later and later.
That's okay, we'll adapt. Glenn and I have been talking about sort of a new push on member events at the clubhouse, like the Messier Marathon, like the Double Star Marathon or mini Messier Marathon. So as the weather gets, as we come out of winter, watch for these sorts of things to try to inspire folks, like a small scope star party, like nothing bigger than like 4 inches. Let's go out and see what we can see with those. And we'll want to do more to get people out to the clubhouse and just out in general, looking up at the sky. So take advantage of every clear night you can. Some nights you can't because you're tired, work, kids driving you crazy, whatever. But as often as you can get outside and enjoy the beauty of the night sky, and
Amen.
that's what it's all about. All right, I think that's it for us. We've been up here way too long. Come on, let's go.
You're okay.
I get to run in a minute.
Thank you, Glenn and Rich. Introduce our speaker, Dr. Gabor Furesz. We'll be talking about LLAMAS, the 2,400 little eyes for one big telescope. Dr. Gabor Furesz had an early start with do-it-yourself amateur astronomy. By the age of 10, with support with his parents and teachers, went on to grind and build his own telescope, learned how to process his own film and darkroom, and eventually built a CCD from a construction kit. And he went on to earn his PhD in astrophysics from the University of Szeged, Hungary. Oops, typo there. And he actually spent some time here at the CFA as a pre-doctoral fellow, working on instruments for the 6.5 meter Magellan telescopes. And currently, Dr. Furesz is a principal research scientist at MIT Kavli Institute, where he's worked on TESS and now LLAMAS. And LLAMAS stands for Large Lenslet Area Magellan Spectrograph. It'll soon become a workhorse for follow-up spectral observations. It consists of 2,400 micro-lens-fed fiber array, almost like an imaging chip, but instead of pixels, it's individual fibers in each. And those fibers are split between 8 separate spectrographs, employing 24 extremely fast f1.05 cameras. So we get the inside scoop of the design, the development, and the ongoing build for something very nearing completion. So it's very exciting. We may have a little setup time. Let's see.
All right, well, welcome. Thank you for hosting me. I don't know, I have a tendency of talking long, so just cut me short when you're like, oh, no, this skip. I have lots of slides, and I will just sometimes ask, can I go? And then I will just be quick. And someone there's in the room who actually knows all the details of this, because he worked in the camera design, I just realized. And so he might catch errors and say, hey, Gabor, that's not how it works. So just keep your all right, so let's get going. So this is basically the talk outline. I'm gonna give a little bit of a personal introduction so you know who I am, where I'm coming from. Then we talk about spectroscopy in general because, well, you all hopefully are observers and have a telescope, but spectroscopy is something that hobby astronomers don't get into that much. But some of you do. And so we'll review a little bit spectroscopy and look at some science applications. And then we'll look what the conventional old-fashioned tools for spectroscopy were and how it evolved into something what we call three-dimensional spectroscopy or integral field spectroscopy, or some call that hyperspectral imaging, depending on which part of the science or industry you are in. And so one specific realization of that is going to be this LLAMAS spectrograph that I'm going to talk a lot about, how is that happened. Okay, so I started when I was 10. That's a picture I'm not going to put on a dating website ever, but I'll show it to you. And so you can see it's like a theodolite little mount replaced with like a telescope, which was like 3 inches in diameter that my dad helped me to build. And then, you know, it's very minimalistic, but it helped me to get started. And so where was it? So we're on that side of the big pond right now. I came from this side of the big pond, from over here. And then, well, you know, these days, that's not a fun part of the world, what's going on here, which is really sad, and also what's going on there. Let's not talk about that. But the little town where I come from, that's like 100,000 people who live there. It's a very neat town, and what's most neat about it, it has a public observatory, and it's on top of a building that is for all sorts of educational activities, and that's where I joined as a not even teenager and started doing all sorts of things there. And then, of course, I wanted to do more, so I built more telescopes. I did grind my own mirrors, and I started drawing because back then, well, that's what I had. And so I was also doing astrophotography on film. Many of you here, I can tell, you know what film is. These days, you have to say it's like film is like a thing that not everybody knows. And so I was really happy doing that, but I wanted to do more. And I know you saw those HSD images and like, oh wow, can I get closer to that somehow? And so that happened of, you know, doing some more observing and then doing some really, really early CCD imaging. And that means early, again, any of you know this book? Yeah, any of you know this book? Yeah. It was really hard to get in Hungary because that was just after, you know, the Soviet Union kind of get out of Hungary. And so it was a very different world in there, but I could get, luckily, some of those TC211 chips and the TC245s. And so not just that, but we have sort of like a nationwide astronomy community in the Hungarian Astronomical Association, and we have like a sky and telescope, like a little monthly called Meteor. And then it had an astrophotography column. And so in mid-90s, we changed that to digital imaging column. And I was leading that column for a good decade and a half. So this was like the first article when I was like having my first cookbook camera images. And, you know, that's the only picture I could dig up from that old system here, which is, you know, I machined it all. I learned how to learn late as a teenager, and then I did all the bits and pieces. So it was a lot of fun. And then with that, I went to university. The university has a small telescope, relatively small. It's 16 inches, so it's not that small. And as a thesis project for master's degree, I did build a little spectrograph. And luckily, that university has connections, so I ended up in the DDO up in Toronto, where I could use a larger spectrograph and a larger telescope. And that really got me hooked up like, oh, I really want to do more. And so the tools back then in the early 90s were, you know, compared to today's CAD modeling tools, were very minimalistic. But actually, it was a really, really good training ground. And in Hungary, we had access to very little funding or no funding at the university. So it's not like you had access to an interferometer like I do now. So I had to build my own little, Twyman green interferometer, and then again, still machine all my work parts. But that led me here exactly. In 2002, I had a visit from actually a Toronto trip, and then I met some of the folks here who still work here. And I showed them what I do, and they were like, "Oh yeah, we build instruments. Do you want to come?" And I'm like, "Sure, I do." And that's how I ended up working on instrumentations for the MMT, which was a lot of fun. It sort of seems like it's like moving away from the hobby astronomy. Yeah, it became my profession. I became staff astronomer here, and then I went to MIT, where I was research scientist, and then later became principal research scientist, and worked on ground-based instruments for the 6.5-meter Magellan telescope, which is in Chile, and then got to work on some space things, which one of them was TESS, which Josh also worked on like quite a bit. And then that was really interesting because there were some moments in TESS, and now it's like, it's all good because TESS has worked beautifully, and they did all sorts of great things, but I tell you, there's like something when, these kind of headlines come out, you don't want to see them. And TESS almost had a Hubble problem, but thanks to mostly actually Josh there and some other many, many folks, that got solved. And I got into that because I built sort of the star simulator for TESS, which was projecting star images in the lab into TESS to make sure it works. And when TESS didn't work, the first thing was like, "Oh, your star simulator sucks." I'm like, excuse my French. And I'm like, I don't know. And so there was a lot of back and forth, and then there was, tens and hundreds of people who worked on TESS, but then tens of people who solved that problem. And so that's the point that I was trying to make here, and in my little introduction for the talk that I sent around, is that projects like this are awesome, but you only get such a small slice of the puzzle because they are so big projects, and then one human can only do so much. So yes, you sometimes even get to touch the thing that goes to space and work on some aspects, but not the whole thing. And hobby astronomers, we like to oversee a whole thing. When we build a telescope, we like to just do it from the very beginning to the very end, use it. And so that's a different thing, and you can't do that in a project of that scale like TESS or a giant telescope, or not to even mention James Webb. They all bring beautiful results, but they're a little bit getting removed. So what I want to talk about here is a smaller scale project, which might still seem a little bit, too far removed from this room, although I would argue it's not, because it's just happening down the street. And by the way, if anybody wants to do a lab tour and really serious about it, we can talk. And Corey has already been in the lab. I was trying to recruit him. And so we can set up some lab tours there. But with projects of this size, you actually still work in a small team of 6 to 10 people. Right now it's too small. That's why I tried to recruit him, because 2 of us only, which is not enough. But you get to do everything. And I mean, really, really everything. Sometimes you don't just drill holes and tap holes and not just, use a $100,000 interferometer, but all sorts of things, the whole scale, the whole spectrum. And so with that, let's start talking about a little bit of science and the other kind of spectrum, the real electromagnetic spectrum. So as I said, many of you do astronomy, so some of these slides are something that I can just skip. You know what an electromagnetic spectrum is, you know what the different wavelength ranges are, that we mostly use that visible portion of it. It's a visible because the output of the sun, which is that essentially that orange curve there, is a black body output, which is the same temperature as the sun. That peaks in the visible. That's why it's called visible light, because we evolved to see where the sun puts out most of the light, obviously. But then when you actually disperse the light from the sun and make a spectrum, you actually see spectral lines. So what are these spectral lines? Well, they can be absorption lines or emission lines, depending on exactly how they are created. If you see a light source through a cold gas cloud, then they become absorption lines. If you see scattered light coming out of a gas cloud, which is light exciting the atoms in the gas cloud, then they can re-emit some of that excitement coming from the energy of the light source and becomes emission features. And again, back to some basic physics. You probably all know that, we don't have to talk about it, how the different spectral lines are created and why they are distinct lines, because in the structure of the atom, electrons tend to have distinct orbits, if you want to call them that way. And we're not going to go into quantum physics, so the point is that there are distinct spectral lines because the structure of the atom is not continuous, but it has distinct features. So spectra can tell about a lot of things. It can do, chemical analysis because these different spectral lines are very closely tied to the structure of the different atoms, different chemicals. So when you see a structure of complex line, you can do chemical analysis. You can do it, not just in stars, but like, in forensic science. If you look at an ink and you take a spectrum of an ink, you can trace down where a given pen was made, for example. So spectroscopy is useful, near and far. But let's stick to the far part. And so when you look at a solar spectrum, which is, again, as usually plotted, is wavelength on the horizontal axis and intensity on the vertical axis, there's actually a big difference of how a solar spectrum looks outside of the atmosphere, which is blue, and then how it looks on the surface of the Earth, which is the red one, because the atmosphere puts on a lots and lots of absorption lines. And so some of the absorption features are the same in the visible because, well, they are coming from the sun, but some of them are telluric lines which build on top of the spectrum. So we can learn a lot about the sun, but you can also learn a lot about the Earth's atmosphere this way. And some of these studies, of course, you have to go and do outside because not every single wavelength reaches the surface of Earth. That's how you build satellites. And TESS didn't go up there because it didn't see in the wavelength range, because TESS was a visible wavelength emission. It went outside of the atmosphere to get even more sensitivity, and also in order to get rid of some other annoying bits of the atmosphere. So we can learn a lot about stars from spectroscopy. So it can be, chemical analysis. We can, assign different types of the stars, which this building particularly, or well, this institute is very famous for. We can create all sorts of great science. We can define the main sequence of stars, and we can sort through lots of properties within the stars. And all of that information is coming from a spectrum. Now, this is a relatively high resolution spectrum, so it's stretched so far that it's sliced and then sort of reformatted to be on this single picture. It's also, if somebody is familiar, it's called an Eshel spectrograph that makes this kind of image. And there's a lot of information in that. Someone who is familiar with spectroscopy can say, oh yeah, hydrogen alpha, oh yeah, there's sodium going on there. And then, oh, there's magnesium and all sorts of things. You can just point what is what. You didn't catch that. So
We knew that.
And then, and then you didn't catch me also because I said an image, and I can tell you that, oh, it's not an image. That's actually a movie. Because what happens in a spectrum, and you can do all your sort of chemical analysis, but then if you look really closely, this kind of thing can happen in a spectrum. What does it tell you? Well, it tells you even more. And this can be a sign of motion, because whatever is out there and is moving and emitting some sort of radiation, that radiation gets subject to the Doppler effect. And so what a Doppler effect is, again, most of you probably know, is that if your moving object that emits, in this case, light, moves and periodically comes towards you or moves away from you, when it moves away from you, all those lines shift towards the red part of the spectrum. When it comes towards you, it shifts towards the blue. This is true for sound waves as well as for other electromagnetic waves. And so what is it really useful for is what the last 2 decades have been in astronomy, or not all astronomy, but most of astronomy, is about exosolar planets. And again, TESS was a mission which went out to find, identify planets, not by this method. It's a different method. TESS used the transit method because that's what you can do on many, many stars at the same time, like the Kepler Space Telescope did. But then it only sort of a transit when the planet goes in front of the star and obscures part of the star. the dip in the light curve is only proportional to the size of the planet compared to the host star, but it doesn't tell you anything about the mass. The mass comes from these kind of measurements, which is a spectroscopic measurement due to the Doppler effect. Those are actually really tricky measurements because this, when I show it's a movie, I really exaggerated. These kind of Doppler measurements are very, very tricky because the spectral lines are really measured only in a few pixels, but the Doppler motion in the spectrum is actually, anybody can guess how much? Yes, it's a 10,000th of a pixel. Yes, so you have to measure 10,000 lines at the same time in order to detect it. So it's literally a few silicon atoms worth of motion on the detector that we are measuring with some of these instruments. And CFA is building one of those for the giant Magellan telescope, called the GTOS spectrograph. So probably you can have someone talk about that at some point. It's really cool. Okay, so now we can measure motion with spectroscopy. So it can tell us about a lot of things because everything is in motion in the universe. And so you can go from the nearest object to the farthest object. You can go to these galaxies, and they are all going to be moving. And so what you can do then is that you can create somehow an image or do some measurements of a galaxy which looks like this in a picture. But then if you could replace that picture, which is just a two-dimensional image, with information of movement, then it can give you this three-dimensional view, this kinematic view of the galaxy. And this is what it's done here. This was done by an instrument called MUSE, which is built by the European Southern Observatory, and it's done in Chile. And it's kind of a three-dimensional spectrograph that I'm going to talk about. And this can give you a picture like this, because what it does, it doesn't just take an image, but actually takes an image in a way that from every single point of the image, you can pull a full spectrum. So you can essentially, per pixel, tell what's happening. The whole chemical analysis that we kind of looked at very briefly, as well as the
ring galaxy?
Sorry?
Is that a polar ring galaxy?
I am not so sure.
Okay.
Because MUSE has a very, very small field of view.
Yeah.
But to be honest, I didn't check which object. I just grabbed the MUSE image to illustrate this.
Okay.
And so here, the color coding is velocity. Red is moving away from you. Blue is coming towards you. So you can clearly guess what's going on here. What's going on is rotation. And that sort of you expect. Now, the cool thing about these kind of rotational measurements is that what actually got us to know about dark matter, because if you do these kind of velocity measurements on a large galaxy, and you start to measure rotational movement away from the core. So this is distance away from the core of the galaxy, and then this is how fast things are moving. Then this is what you see, and what you expect is sort of this curve. Everything close into the galaxy's core, they move fast, and everything farther out just slows down. Just like in the solar system, Pluto goes really, really slow. Sorry, I like Pluto. I still use Pluto as an example. And then Mercury goes really fast. And so the thing is that this is not what astronomers found. They can identify objects all the way out here that still belong to the galaxy based on its redshift, so we know it's the same distance. Then what they see is that, oh, actually things out here, they are moving faster. And then when we don't see objects anymore, they can look at with radio telescopes at the 21 centimeter wavelength of hydrogen, because the galaxy actually extends far beyond this. We'll learn more about that in a little bit. And then those measurements tell you that, oh, there's even more mass that has to be in there. And that's only possible if most of that mass, 90% of it, you don't see. And that's dark matter. So I think by this point, I convinced you that spectroscopy is a very, very, very useful tool. Now, how you build a spectrograph. And so some of you might have used one or even built one, but let's just very briefly look at the anatomy and the working principle of a spectrograph. And so what you need is, you have some sort of image, and you have to have essentially a telescope that collects a lot of light, because spectroscopy is going to, disperse that light. So if you look at faint objects, which we do, dispersing that light is going to make the dispersed light, the spectrum, even fainter. So you need a larger telescope. And then that light gets, after the focus of the telescope, collimated and goes through a dispersing element. and then a camera that refocuses the beam, but then these beams are colored, different colors for different direction, and so they get focused to different location onto a detector. This is a basic spectrograph, but then the problem is that if you just put a spectrograph behind a telescope right away, then this is kind of what you get. And so everybody recognizes the Lyra ring nebula here. And then the problem is that when you do not block light from the telescope focal plane and you let every single object into the spectrograph, then what happens is that you can identify the stars. These are very low resolution spectra, so you can see the 0th order image, what we call is a straight through image. And then you can see correspondingly that those stars have their spectra. And you can see if there's a location of one star versus the other, then the spectra kind of correspondingly starts with the same offset. Now, there's a ring nebula. The ring nebula doesn't produce a continuous spectrum because it's an emission, so you only see sort of light at certain wavelengths, so it appears as multiple images at different wavelengths. But what really gives you a clean image is when you can put a slit onto the focal plane of your telescope and essentially block the light from anything else except the object you're interested in. And then you can have a clean spectrum, and then you can just see the information what you want to see, so you see the clear emission spectral lines of the ring nebula. Now, you can play this sort of trick on Saturn, for example, where you can put the slit on Saturn, and since Saturn is rotating, what you would expect is you would catch this rotation. And indeed, you do, because what you see here is that respect to a straight line, the spectrum of Saturn is full of tilted lines. And why is it tilted? Because, well, this part of the ring, and then Saturn itself is rotating and it's moving away from you, and that part is coming towards you. So the bottom of the lines along the slit, they are essentially red-shifted, and the top is blue-shifted. And so you have these tilts of the spectral lines. Everybody is with me so far? Am I going too fast? Good. Now, but the problem is that you don't see the full Saturn, you just only see what the slit is covering. So if you want to have sort of this full picture of Saturn, the whole spectroscopic story, you have to move your slit a little bit to the right, a little bit to the left, and you sort of have to map out Saturn. So you do two things this way. First of all, you disperse the light, so you have to use longer integration times to capture that long slit spectrum, and you have to take many of them in order to cover the whole picture. So it gets you a lot of information, but it uses a lot of time. However, this is a method that has been used for a long, long time, and it's called long slit spectroscopy. And what it can give you, as we said, we can put a long slit around a galaxy, and then we can recognize that there's a lot of structure going on, so it's all dynamic motion. But what you can also do is that you can take a telescope and then say, oh, wait a second, I can maybe put multiple slits over some objects of interest. And then I can create a spectrum which records multiple spectrum at the same time on the detector, because typically our detectors are not elongated, but like squarish or rectangularish on our digital cameras. So it has the real estate to record more than one single strike of light. And in fact, it's great, and people have been done this for a long, long time. They build these slit masks, so they take images of the sky, they identify interesting objects, and then they laser cut or some sort of way make a mask which only has slits in the right location and right orientation. And then they put the spectrograph behind it, and it creates a spectrum of many objects at the same time. So it increases efficiency. Another way of doing this is an instrument, the actually example I'm using here, that was built here at the CFA. The PI was Andy St. Georgi, and it's called Hectoshell, which was on the MMT, and that's what I did my PhD thesis on, building it and using it, is that you can use optical fibers. What you can do is, on the telescope focal plane, you can place a bunch of optical fibers like this, and then obviously there's going to be an image projected to that by a telescope, and then these fibers are pulled by a robotic arm and placed over certain objects of interest. And then the fibers run into a spectrograph, and then the spectrum is created in the spectrograph for all of the objects at the same time. This is just a close-up of those magnetic buttons that the robot can grip and then place wherever it needs to get placed. The nice thing about this method, this multi-object spectroscopy, is that when you have a slit mask and you put the slits where your objects are, the problem is that typically, if you want to have a lot of objects, it requires a lot of slit size or long slit plate size, and your spectrograph has to be able to take all that in. So you need a big spectrograph. Whereas with fibers, even though you can place those 300 fibers over a plate this big, which that is, you can bring all the 300 fibers into a tiny, very long slit when you arrange them tightly next to each other, so your spectrograph can be proportionally smaller. So it is even more efficient. But astronomers want more, of course. Can we do more than that? And so you guys probably do that already, because narrowband imaging is a thing, both for nighttime and for daytime astronomy. And then these are images you can take from your backyard by one of these H-alpha solar telescopes, and then you can also get a Gaussian H and K filter. And so what you can do this way is that you can get a full detailed image, although you're only looking at one small portion of the spectrum at a time. But if you have many, many filters, you can actually sort of arrive to the same thing, which is what we are after, what's called a three-dimensional data cube, where you have a resolved image in XY coordinates, which is your detector coordinates. But then for each pixel, you actually have a full spectrum. And as I said, you can arrive to this, in multiple ways. You can do long slits along something and then create a long slit spectrum, or you can do narrowband imaging and then sort of build up the wavelength space that way. But can we do it all? And can we do it at once? And so the answer is yes, we can. And this is called three-dimensional or integral field spectroscopy. So far, so good. And so how can you do this? So one example that you can do it is that you take the focal plane of the telescope, and then you somehow have to create space for all of your spectrum. And then what you can do is maybe you can put, instead of a detector onto the focal plane, you can put a little Lenslet array, which pulls those larger square sections of your image into small sections. And then you put a dispersive element and you rotate it, so the spectra, as they fan out, they don't overlap. If you would have the prism or grating with its dispersion axis horizontally, the spectra will overlap and you have confusion. You wouldn't know what's happening. But if you slightly rotate that prism or grating, then you can achieve to something that is still distinguishable. And then this is a real life example of one of those designs, and this is how it looks like on the detector. The problem with this is that you only can make these traces so long because you want to have the two-dimensional image at the same time. So it works for small resolution. Now, how about those fibers? We talked about hectoshell. Yep.
By small resolution, you mean small spectral resolution?
Small spectral resolution, yes. And so spectral resolution is defined by a very simple equation, which is lambda over delta lambda, where delta lambda is like what's the smallest wavelength range that you can distinguish, and then at lambda what wavelength. So, for example, when you do H alpha, you usually have like an angstrom bandwidth filter, something like that. And that's, of course, at H alpha, so it's 6,500 angstroms. So the spectral resolution of that filter, so to say, is 6,500. Here we're talking about resolutions of a few hundred, not thousands, for this kind of spectroscopy. Very often astronomers want more. For measuring those tiny movements of exoplanets, you want 100,000 spectral resolution, so you would have to stretch your spectra quite a bit. But a lot of the intergalactic motions are happening at so high speeds that only a few thousand resolution is sufficient, but a few hundred isn't. So how can you do that? So what you can do is you can use those fibers that we mentioned with hectoshell, but instead of just sparsely putting them over a large area, what if you bundle them up very, very tightly? So you can build a fiber bundle, which is just a really, really tight bundle. And then on the other side of that fiber bundle, you can just arrange them into a long slit, because again, the spectrograph will make long stretches of light, so you cannot have two fibers next to each other. They only have to be, say, in a vertical column in order to get clean spectra. And then you can get clean spectra, and again, you can get your data. And so this is that sort of a method where you have your fibers. The problem with fibers is that even if you build them in a tight bundle, if you ever work with fibers or know how fibers work, you know that there's a core area of the fiber surrounded by something called the cladding, and it's only the core that is guiding the light. But the cladding is essential. Without that, there's no guiding light in the middle. But there's a dead area in terms of light guidance, and so when you bundle them, they also circle, they don't exactly touch, so you lose light. So you don't have a good fill factor. And what you can do then is that you can do a micro lens array that is actually 100% fill factor, and then pulls the light into those fiber cores, and then you have a sparse fiber array with a micro lens coupling. Now you kind of see where the LLAMAS thing is coming from, because LLAMAS is, again, a large Lenslet array in Magellan spectrograph. So it has a large Lenslet array and a fiber array, and it goes into the Magellan telescope. So we're going to talk about this sort of solution for the three-dimensional spectroscopy. But in order to give you the full picture, I have to tell you about one other method, which is called image slicing. And so what you can do is that, can you do something like putting a special optic in the focal point of your telescope, which slices the image and then sort of sends those images into different directions so they don't overlap in the dispersion direction, and kind of reformat them. It's an image reformat there, and then put them on a long slit and then create spectra. And so yes, with all sorts of fancy machining capabilities now with diamond turning and essentially contact bonding, you can make a stack of mirrors, which are very, very thin mirrors, like razor blades on top of each other, and each razor blade is tilted a little bit. And so projecting the light onto it from the telescope and using an array of other mirrors, you can reformat an image. So you can take the image of that galaxy and then put different slices of the galaxy next to each other and create a spectrum. This is another example of such an image slice.
Wait, so is that a piece of metal, or what is that?
So this one is a piece of metal. So this one was diamond machined. But then you can also have glass plates, which you polish so flat that you can essentially just contact bond them at the right orientation. And then you polish the edges of those very, very thin slices of glass. And so these are very unique, and some places can do them really well, like the French do them really well. When you do diamond turn something, the problem becomes is that diamond turning is really good these days, but still not that good. It leaves little grooves on the surface. And so below a certain wavelength, the scattered light becomes too much. So typically those can be used below 400, 450 micron, nanometer wavelength. So below greenish light, so blue, not this work. You have to post-process them, and these little things you can. These are a millimeter or less on the side. So those are very, very thin.
What's the area of that?
So this would be something like an inch by an inch and a half, or even less. Yes. So those are very, very fine things. Well, we're going to talk about lots of fine things, and this is not lab snacks from Tor Labs, but yes, fibers. Fibers are good for your diet. It's not to eat fibers, but it has some fibers and some of the images that I show you. It's in the box, and you can look at it later. The fibers are sticking out. Okay. Still good? Okay, good. Let's keep going. So LLAMAS is, as I said, is this kind of a design, and then let's see how we can build it. But first, of course, you have to find money for it, because these things get expensive.
The previous design with that bunch of mirrors.
Yep.
Is that an alternative to
Yes.
this?
Yes, that's an
Not
alternative.
Part of this. It's not another thing that's going to be part of this.
No, it's an alternative solution.
Okay.
So I try to offer three different ways of doing the spectroscopy. One is the Lenslet array, and then some tilted spectral element, the fiber bundle, or the image slicer. So these are the three different methods. And then when you build an instrument like this, you justify why you choose a given method. And in our case, we wanted high enough resolution, so the Lenslet array coupled just with the dispersion lamp was not enough. And then we wanted to go blue enough And so the image slices were not an option because we wanted to go down to 350 nanometers, so near UV-ish for the science space. So you got to find the money, as I said. And so the instrument I'm going to talk about, that was built over 5 years, and it's about $7 million. Then all said and done. So these are big instruments and expensive instruments. So you got to find the money. So you got to tell your funding agency, that's where you start off, like, why do you want to build it? Well, why do you want to pay for you to build it? And then you can say things like, okay, so here we are in the era of LSST, the Large Synoptic Survey Telescope, or the Rubin Observatory, now it's called, which is gonna map the sky every 3 days to whatever magnitude, and it's gonna discover all sorts of transients. But just discovering something doesn't tell you what it is. For that, you need spectrum, so you need follow-up. And then you say, oh, so we need spectrograph in a large telescope, but we are gonna have lots of these things, so we don't have time to fiddle with them. And so when you look at how a modern spectrograph works with a modern telescope, is that, yeah, you find the object, you see the telescope, you identify the object, you correct your wavefront error, you start your guide there, and then there's a lot of time passed, and you make sure you're on the right object. So there's a lot of time passed before you take the first integration of your spectrum, which is the green bar. So it's like 12 minutes in. And so if you try to follow up spectroscopically a lot of objects at night, every time losing 12 minutes is a lot of minutes. So with an IFU spectrograph, you can say, oh, we don't care about this because we have such a big field of view that you just swing the telescope, you take the image, and it's gonna be in there somewhere. You just fish it out later what you want. And so that's an argument, because then you save a lot of time every night. Another argument that you can make is that, well, somebody else built an instrument like this. I mentioned that Muse kind of instrument, and look at them. They oversubscribed. They wanted to use that instrument almost 20 times more than the time was available. And that oversubscription rate in the same time period for Hubble was only 5.4. So you can hey, these instruments are very cool. They have it, we should have it. That's an argument. And then you can become more scientific, of course, and say, oh, so we want to study the interstellar, not just interstellar, but intergalactic medium. We want to know what is out there between galaxies. Is there anything? And then how do you do that? So what you do is that you try to look for something really, really far, like a quasar, and then light from the quasar, as it travels to you, obviously the quasar is very, very far, so the light is redshifted by the time it gets to you. You see that quasar to be very, very far, and its wavelength, because it's moving so far away at the outskirts of the universe, its whole energy output is mostly in the red. But still, there is some output which is now became visible, which used to be ultraviolet, but now visible. And in this visible thing, we know that this doesn't have any features, because that's not how the atoms work. It should be just a smooth spectrum, but it's not. It has a bunch of absorption lines, and it has a bunch of absorption lines because those are imprinted onto this continuum by matter that is in between the observer and this quasar. But often you don't see these quasars too well. You have to make sure that you understand what the quasar is and where is it. And sometimes these things not just are in absorption, but in emission, which also means that unless you are tuned to the right wavelength, you don't really see them. If you're trying to look at broad wavelength, you don't see them. So the IFU is good. So this is cartoon, and this is an actual spectrum of 3C273, which is well known by probably all of you. And so this is what's called the Lyman alpha break. So this is where the spectrum of the quasar ends. And this should be just smooth sailing or smooth continuum, but it's not. It's a bunch of absorption lines. And so this tells us what's the stuff in between the galaxies. And another way of looking at it is that what if you, so how can you use it? You can use it to tell us what's between you and all these galaxies. But another thing you can use it for is that to determine how big is a galaxy. So this is a galaxy, and you would think that the galaxy is this big. But I'm telling you, no, the galaxy is actually as big as this circle is, because there's still gas that gravitationally belongs to this galaxy, and it's moving around. You just don't see it because it's so faint and it's not really emitting anything. But what it would be cool is that if you find objects that for sure is behind this thing, and you can look at the absorption spectra of those, you can tell how the gas is moving. And from that, you can deduce actually how this galaxy is forming. Because as you go farther and farther out to the outskirts of the universe, you look at early and early stages of the galaxy formation, and you want to understand how it happened. And so all this gas that you don't see is moving and somehow forming the galaxy. But to understand that, you got to figure out how it's moving. So what you can do very, very painfully is that you can do spectroscopy on all of these objects, one at a time, and then decide which one is really far, which one is behind. So you can take this spectrum and say, oh, we see this magnesium absorption line, and so based on that, the redshift of this galaxy is 3.4, so it's behind the galaxy, it's really far. And then you can collect the good ones that you want to look, and then you can start taking a spectrum which actually tells you something about the gas, because to decide where these things are, you have to observe the infrared, but for the actual velocity structure of the cloud, which is associated with the galaxy, you have to work in the visible. So you have to use two different instruments. It's a long process, a lot of telescope time. Wouldn't it be nice if you could just take like a spectrum of every single point and then just start fishing? It's just take one exposure and then go and write your dissertation for the next year. And not hog that telescope and let somebody else use it. Wouldn't that be nice? And so, so that's what we pitched, and that's what I said we're going to do. And then, of course, we still try to like justify to the National Science Foundation of why we can build this and why our approach is good. And so there are lots of different instruments out there which attempt the same, so you have to distinguish yourself from them. So you sort of create some quantities where this is like how many independent samples you can get, and there are instruments out there. You probably heard of Virus, which can do a lot of samples because they have a lot of fibers. But then also the other interesting piece is like how detailed of an information you can get. What's your spectral resolution? And then you can see that, well, Virus might get you a lot of information, but not so deep. And so in this map of instruments, the MUSE instrument, which I use as an example, sits in the far right corner. So that's the most amount of information. And so that's really great, but it's also $40 million. So what we were saying is that, well, we can build something for you which kind of sits there, which is getting towards there, but it's a lot cheaper. And they liked the idea, so they gave us money. And then we told them, we're not going to build a MUSE because that's a picture of MUSE. It's a really, really complex instrument. Anybody? So we're like, no, we're not doing that. We're not doing that. So we went in a different way. This is an eye chart, and so I don't expect you to read it, but so what I'm trying to do from now on is just like walk you through in the next, do I have 20 minutes? Is that okay? Okay, so I'll try to hurry up. In the next 20 minutes, what I will try to walk you through is that how an instrument gets built from the very beginning. We already started, we are the funding phase. How do you get the funding? How do you convince the funding agency? And then how do you go from there to, here's the instrument, let's turn it on. So what you do next after they give you the money is that you sort of make a flow down from the science case that you made to like something that you can tell an engineer to design to. To an engineer, you cannot tell, I wanna resolve the interstellar medium with this resolution. The engineer would like, okay, go ahead. An engineer wants to like, build me this long, build me this heavy, build me, something. So we have to translate all this great science we sort of talked about into some numbers. And so from this, you kind of go into a system definition where you kind of tell, okay, what do I want? I have to tell, what my observing bandpass is, because that's going to determine what kind of glasses, what kind of detectors I use, the field of view, so, how many spectrographs will I need, the spatial and the spectral resolution, how fine of a pixel size, what is the actual pixel size of the detector, or if I use fibers, how big those fibers are. And so all that science on the top sort of defines your system, and then that system you start to break down into subsystems and individual parameters of like, how big, how heavy, etc. So you do this, and then with that you sort of start conceptualizing of like, how are you going to build this? And then, so this is your, toy model or build it out of Lego first. And then you start playing with some optical designs of like, okay, I'm going to have a fiber which puts out a light, and then I have to collimate that, and then, oh, I really want a wide band pass. I can't really handle that because it becomes really hard to design a camera that works from the UV to the infrared. So I'm gonna have a dichroic to split into red wavelengths and blue wavelengths, and I'm gonna build a camera that works only for that. So it's a shorter wavelength range, so it's easier to make the camera apochromatic over a smaller passband. He's a really good optical designer, as you probably all know. He did a lot of the analysis, double checking my work and then making sure that it's good and improved some of that. So thank you, Josh. You start with these, and then you of course have to start telling your mechanical engineer something of like, hey, this is what we are thinking of. And then when you design this instrument, obviously you can't do it all on your own. You'll need engineers. So you who is the instrument scientist, sort of understand the science and the requirements and what it means, but then you have to direct engineers of like, okay, you're gonna do this, you're gonna do that. And sometimes your engineers comes back, you can't do that. Think of something else. And then you kind of rearrange things. But so you need mechanical engineer, electrical engineer, an optical engineer, and you need a software engineer, you need graduate students to do the actual work, and you need to pick companies. And so there's a lot of people and moving pieces. But the fun part is for someone who gets to become the instrument scientist that you can actually oversee all of this. Unlike with these big missions that I mentioned, where you can maybe touch one little part, here you can really and have to touch all of the parts. And so I'm showing you this conceptual design because the final instrument looks very different. And early on we were like, okay, so here's the telescope, where are we gonna put it? Oh, let's put it on the back of the telescope into the Cassegrain focus, and then let's build something that has many units, and these little spectrographs with their red and blue arms, the red and blue cameras are kind of like hanging down there like fruit. And then in order to get a large field of view, we just build a lot of systems. Because what you're thinking there is that, oh, I'm gonna have thousands of fibers, so I either build a spectrograph which can take them all at the same time, and they have lenses this big, and then your lens manufacturer says, can do. Or you can say, oh, why don't I build them very small, because then I can make quantity, and then industry likes quantity, and maybe it's gonna pay off because I have my design cost once, and I make it over multiple times. But then if you make it too many times, you're like, oh, wait a second, but someone has to assemble that, and then you're gonna pay labor for assembly, so you're gonna try to figure out like how many you want. And so what you do next is you do these trade studies. You do trade studies at system level, and then you look at other instruments who build spectrographs, and you are like, I don't even know how I'm gonna call this thing, and then let's see how does it fare with others. Oh, they use the beam diameter of this big. Can I get away with smaller? Oh, their cameras are really fast, that's scary. Can I just get this? And then, oh yeah, I probably can't afford that, but I'm still gonna do like 64 of these. And then you start thinking, but this thinking will evolve over time, and then you finally end up with some parameters that you like. And then again, I don't want you to necessarily read all of that, but the point is that you sort of at the system level, you define your thing, you lock in your concept. So you have your preliminary design, that's what you call it. And then you are gonna then fix this and say, okay, that's what we are building to. And then at this point, it's good to just do a sanity check of like, okay, there are others who build similar instruments. Are we still worth building? Are we still offering something that others don't offer? And then you say, oh, yeah, Muse that we mentioned so many times, that doesn't cover the blue below this wavelength in angstroms because they have diamond turned things. So, okay, we can do something because they can only see things which are redshifted far enough that it falls into that wavelength. When the Lyman alpha from the UV goes really far, that's redshift of 2 and beyond. They can't see the relatively nearby universe. If we build something that can see in the near UV, we can see the Z1 to Z2, so redshift 1 to 2, so that gives us something that they cannot do. So you do this kind of sanity check, and then you go back and say, okay, let's then break it down into subsystems and then design a camera. And then at the moment you're looking at something like this, and like, oh, it's an f1.1 camera. That's gonna hurt. And then you say, okay, well, let's do some more trade studies. And then again, I don't want you to read all this, but these, slide after slide is just like, it's a thinking process of like, oh, I want this, that means that, and then that leads to this. And then you kind of break it down and you're like, oh, dead end, back at the beginning. And then you keep figuring out what you want. And ultimately you're like, okay, it's gonna be an F1 camera. There's no way out of it. And then you go to literature and then you see who else did one, and there's all F1-ish cameras or near, and you're like, yeah, I don't know, this one has a central obscuration, and you kind of pick your poison. And then you're like, okay, I'm gonna choose this one and we are gonna go. But then when you decided, since you're always pushing the boundaries, otherwise why do you do that? Otherwise that's called industry. If you're pushing the boundaries, it's called science, and you lose money often. And so you're gonna, okay, well, there's gonna be some risks involved. So you gotta address those risks. You gotta identify which parts are gonna be problematic, and then you kind of try to tackle that first. That's why, Josh. Yeah, so risks. So where are the risks? So one clear part of the risk is that fiber thing and the lenslet array. So if you look at the lenslet in a cross section, oh, it's just a long glass rod with, you know, two very simple spherical curvature things on each end. Yes, but that thing is a millimeter long there. And in cross section, it's like a quarter millimeter. So, you know, 10 mils. So that's tiny, and you need like, you know, 2,400 in a bundle of them. So can somebody build that? And then also you have to plug your fibers, and you have to have your fibers in a very, very regular grid. So can someone make you a plate where you can plug your fibers they are kept in a regular distance, and then put the microlens? So you're like, okay, let's not build 2,400 first. Let's just build, you know, like a couple hundred. And then let's go to industry and say, hey, can you guys do that? So you make your drawings, and then you put all sorts of tolerances, and then some of you are like, oh, that's a 10 micron tolerance, and yep, and then even smaller sometimes. And then you spend some money, and then you got some parts in, and then you build a whole thing so you can look at what you're doing with a microscope, and then you have some manipulators, and then here's a glass plate which has a bunch of holes, and then there's a fiber that's like, okay, let's plug it in. Let's see if it kind of holds in there. And so if we zoom in that little section there, then it's like that's how it looks under a microscope. And then you have these little holes, and then your fibers come from the top, and there's a pipette, a micropipette, which nobody makes, so you have to make your own to kind of put the glue in there and then bond your fiber. And then once it works, then you look at the back side. It's like, oh, the fibers are true. Okay, these are the empty holes. These are two fibers plugged in. Okay, so they come through. They are clean. The bond didn't cover it, so it's gonna work. But then you're like, oh, wait a second. Let's look at those fiber faces. You all know about telescopes and interferometers and what a good quality optic is. This is a really good quality optic, even though it's like 4 mils across because it's 100 micron across. That's a face of a fiber. Because those fibers, they have to be made. They come in a long, you know, tens of kilometers spool, and you have to cut them to length. But when you cut them, it's going to be nice because it has to be nice. It's a piece of optic. Your light goes into it. It's important. So you figure out a way to cut them, but then make sure that it's flat. You're going to put it under a microscope and an interferometer, and like, oh, it's mostly great, but there's some stuff going on there. And why is that? Well, that's from your process of cutting and slicing it. It's called cleaving. But it's okay because, as I said, the fiber consists of a core and a cladding, and you don't really see it distinguished, but the core only starts all the way here. So all of the stuff that is not nice is outside, so it's okay. But then you say, oh, is it really okay? So here's another example where we made sure that the core and the cladding is visible, and you're like, oh, but is my process of cutting the fibers, because I make 2,400, is it gonna be constant enough? Or are things gonna change? And so, yeah. The devil is in the details, because yeah, sometimes it's like that, sometimes it's like this, so which one's good enough? And then sometimes you're like, oh, what are those little marks there? And then you figure out, oh, okay, there are a few parameters in your process that you really have to be careful of. And this sometimes requires of taking that little piece of fiber to a scanning electron microscope and like, oh, let's look at it really closely. And then you're like, oh, this is the parameter, a single parameter I changed between these, and this is ugly, that's great. So that parameter has to be tuned for this value and capped at that value, not to ever go this. And what it is really, when you cut the fiber, the stress wave kind of propagates in the fiber like an earthquake does in the crust of Earth. And then if you cut the fiber here, the stress wave starts to propagate, but then they kind of start to reflect back and they collide and they interfere with each other. So if you stress the fiber too much, you can see that the cutting point the waves are so violent that when they collide after reflection, they just mess up your surface. So you learn a lot about tiny, tiny micron-like details, even you're building something for a 6.5 meter telescope. So there's a lot of prototyping. And then we're coming to Josh's territory, optical design. Okay, so let's build that camera. Because that camera is going to have a 70 millimeter focal length. Or you would say, oh, let's just buy a lens from a photo store. It should work. And no, not really. Because what happens is that you have a dispersive element which creates the spectrum in front of it. And so even though your incoming beam might be just 50 millimeter, but it gets spread. And so by the time it hits your lens, it's 67 millimeter. Oh, did I just say I have a 70 millimeter focal length? Oh, 70 or 67? Oh, that's fast. And then you're like, oh, what can I do? And then you're like, okay, it's a spectrograph. The blue and the red line never have to come to focus at the same focal length because they're in different locations. Oh, so I can just tilt my focal plane. It doesn't matter. It's a spectrograph. Oh, good. So, and then you figure out, oh, do I have to make an A-sphere? You do a lot of legwork with the optical design, and you look at your spot diagrams, which you are probably also very familiar with. This is just tells you that different parts of the image that the detector sees, how good your images are, and this is like, oh, I gotta be waved in this. And so, okay, yeah, I met my target, good. But that's just the design. It's not your actual thing, because by the time you build it, well, your manufacturer will say to the, oh, this is a nice design, but I can't, build that to like exactly what it is. Give me some range of tolerances of like the central thickness of the lens. I'm not gonna make it to the micron. I'm gonna maybe make it 100 micron thicker or 100 micron thinner. Is that good enough? And so you have different ranges of tolerances, and of course they also come at different value for your wallet. So you have to pick your poison again. You have to figure out, okay, what am I gonna do? Am I gonna pay more money for them to make the lens ring nice and then just give myself room when I align those multiple lenses, or am I gonna be just really cheap on the optics and just really excellent job aligning them to each other? So you do this what's called a tolerance study, and that's what Josh actually did for us. And you can make sure that whatever your ideal system was, you kind of simulate what your realistically built system is. And you see it's different, but you just gotta make sure that it's still within the range that you want. And then when it's all good, then you say, okay, then good, let's build it. But no, because besides the devils, there are also ghosts. And what ghosts are, so some of you can know, is that within an optical system, you can actually have multiple reflections between surfaces, and they can get defocused images on top of your focused images. So you have to do some more analysis and then maybe change your design around to get rid of those ghosts, because don't like ghosts, don't like devils. And once you're done, you can make production drawings and say like, good. The optical designer is done, at least for now. Here, Mr. Manufacturing Company, make those lenses, and then you pay them $1 million, and then they give you some lenses a year later or more, because sometimes these glasses are coming from Japan and they are like a year out just for the glass. And then you're like, okay, so let's work on the fibers now. And then on the left side, you see a cartoonish cross section of how the fibers are. So the fibers are, as I said, separated from each other. They are bonded into this glass plate, and then they have a microlens array in front of it, which is a double-sided microlens array, which, by the way, has to be like aligned to a micron position laterally to the fiber. So you come up with some way of doing that, and then you find a company who can make you this with all micron precision in glass, and then you learn that, oh, there's a company who can make it in Switzerland, and they're happy to help you, and then they're like, oh, good, they can actually make it. And so you're like, okay, so here's that little glass plate that you see up there, which has holes for 2,400 fibers. And then here, these are the fibers. Okay? So you'll be able to see to the top, because you really need light. I'm not going to hand it out right now because you're not going to see much. And also, these are a little pokey. But so, yeah, so these are the optical fibers, which we have 2,400. And then you see it's a kind of, substantial bundle already. But then you realize, oh, I barely filled any of that. So 2,400 is a lot. And then these are individually bonded in there by a technician. So actually I had 2 technicians, and it took them 9 months to just bond it under the microscope. And I tell you, my best technician
is done manually by hand, fiber by fiber.
Yep. And the fiber has 2 sides, right? So, yep. And the other side has to be bonded too. And it's manually because, yeah, you feed it into that little tube, but then you have to deposit the glue. And then you have to sort of push the fiber down so the glue gets sucked in by capillary forces, but then you have to pull it back so the front side is nice and even, and then you cure it with UV light, and then you manage that. Yeah, so there's a lot of things to do there.
You polish it?
So they're not polished because they are done with this cleaving process, so they are cut under tension, so they're optically perfect. The interferograms showed, and we made all those studies to make sure that they're going to be good.
And so 6 months into the process, now they're working on something that has obviously a lot of effort into it, and they're working on a single thing, and every single one has to be done without damaging any of the
Yep.
previous ones. And
That's why they practiced on this one before they started on the other one. And then even with this one, sometimes it happened that, yeah, fiber broke. And then how you deal with that?
Right.
Well, it's really hard. And so I tell you that I don't like dentists, but I like root canal files now, because root canal file, that's the only thing that can clean that hole. And very carefully, because you can make more damage. But credit to the technicians, they only had like 3 occasions when it didn't break in, but it was like stuck, and then we had to clean holes, and they didn't break a single fiber. And my best technician, I tell you again, he was only actually having a high school degree. He went to college, but he was like, oh, it's not for me. He went to manage an auto parts store in Tewksbury. That guy had the best hands ever and the smartest ever. At the end of the process, I was like letting him run the ZMAX files and doing all sorts of, and he did all the lens assemblies where the lenses had to be built for the F1 cameras. He's working out Lincoln Labs. Guess what? They hired him. Of course, they did.
Quick question.
Yep.
How many of those assemblies in your final product?
So one of this, just one with all the 2400 fibers in. And then these are broken into 8 units on the other side, where they are in a linear array of 300 each. And that's feeding into 8 spectrographs, which I'm going to show you in a second.
But how many of those are you gonna make?
So just one of these units, but then all 2400 fibers are bonded in there. Yeah.
So 300 in each.
And so you have to have the microlens array in front of it, which again, you find a manufacturer who can make a nice microlens array, very, very smooth. And then you can look at the PSF of a single microlens. That's what you want to see. That's really great microlens arrays. And then, of course, you have to start building your spectrographs, because they all have to kind of come together. And then what your spectrograph looks like is something like this. So this is your sort of optical model. And so to understand, so the fibers are sort of in the middle of this, embedded in a piece of glass, which is another interesting story. All 300 fibers create a light cone which hit a collimator. And so 300 collimated beams come back, and then this splits it, lets the red long wavelengths through, and then goes into a red camera. And then the blue and green colored light goes there, and there's another dichroic which splits it into a blue camera and the green camera, which has its own wavelength range. And so again, it materializes like this in the CAD model. You can see the corresponding components, and you can see that physically on the carbon fiber bench, you can identify the 3 cradles which will receive the lens systems. And the lenses are put into barrels. Each of these lenses are bonded into bezels with some elastic, so the thermal contraction of the aluminum bezels will not crush the glass. And then they are put into precision machine barrels and built up with some very, very specialized tools, and metrology done all the time, and everything recorded, and then interferometry done in so many other measurements, and then you slap onto the back a 2K by 2K CCD with a 5-stage thermoelectric cooler, and then you go into production mode. And then because you build 8 of these spectrographs, each have 3 cameras, so it's 24 lens assemblies and 24 CCDs and 24 focus mechanisms. And so you decided that 64 units was too many, but you decided that 24 you can manage over the given time you have. And then you order a bunch of things, and then in the meantime, you also kind of build 1 unit off the side, which you call a full prototype. And you don't want to spend too much money, so it only has 2 cameras, as you recognize, and not everything is anodized, but so you kind of test the full system. And we wanted to ship it down to Chile to make sure that it works on the sky, and we did that, but we shipped it, and the pandemic hit, so it was sitting down there for a year and a half, and we couldn't go, so we couldn't really test it, so we essentially ended up building the whole thing blind without knowing for sure it's going to work. But then we had to ship the prototype back because some parts were unique and we didn't want to buy it again. But then the good thing is that we shipped it to Chile, and then we looked at, the sharp registers, and then sometimes it's so, 15G on the crate, but we isolated it properly. It's still so a couple Gs, but then we opened it back when it got shipped back without ever trying it, and then we turned it on, and it was beautifully aligned and still in focus. So that's good. So we know it's gonna work. So these are the cameras again in cross section, and so this is the images they make. So these are spectral traces of one of the cameras, and then these little windows are like zoomed in versions. So essentially this image just means that this is a zoomed in image from this part. This is a zoomed in image from this part, and so forth. So you can see that from corner to corner it's sharp images, and then these boxes with the very black background, those are the actual models from the optical design. So it shows that you are very, very close to your design parameters. So we're happy about it, and as I said, after shipping back and forth, it all behaved the same way. And so this is when we started with the fibers. That's a human hair. So just to get an idea of these fibers, you'll get to see, but that was the empty plate when we started plugging it, and then those guys just chugged along, and then had the holes covered, not to drop glue in, because then it would be a problem, and then they went one by one. And then this was the backside of the underneath the microscope, so you can see all the little fibers protruding, coming out. And then it went on, and I said the other side of these fibers, because the fiber has two ends, they had to be arranged in a very regular linear way. And it's not just regular, they had to be fanning out. They have to meet something called the Schmidt condition. It has something to do with the Schmidt telescope. So the fiber ends are actually not on a line, but they are curved. So they all have to point from a given point of origin. So we had the same company make a glass plate, a special glass plate, which had V grooves in a fanning out manner. These are the microscopic images of the V grooves. We had little pockets for the glue. And then you can see that they are beautiful V grooves. Again, they are micro precision machine V grooves in glass. And then you bond 300 fibers in them. And that's how it looks like. And then you repeat it 8 times. And then you have your spectrograph slits.
And also, they're not randomly connected from.
No, very good question. Yes, a very, very good point. So they're not randomly connected in a way that you see that this is a very, where's the image? So here you can see that it's a very, very dense format for the spectrum. Essentially, a spectral trace is almost right next to the other one. And you have to, of course, know which part of the image this belongs to. You could map that out. You could just say, oh, I'm just going to randomly build a bundle, and then after that, I'm going to, with whatever illumination, I'm going to point a light into one at a time and then figure out which on the other end and map it. We didn't do it this way. We did it in a way where we knew exactly which goes where for the following reason. In astronomy, when you do go after very, very faint objects, it could be problematic that if you have 2 spectra so close. So for our faintest objects, we wanted to have only every other spectrum. So the way we did that in the 2-dimensional array, we have one corner which contains half of the fibers, which is surrounded by this L-shaped other part, which is 50% of the fibers, and they're alternating each other. So we can put a mask in front of the fiber bundle, a single blade, essentially. Well, it's an L-shaped blade, but yeah, and then that single thing can obscure every other fiber, which will decrease the field of view of our unit, but it will make sure that we have a lot of space between traces to determine and subtract the background. So we did that on purpose, yes. So that's a very good question. And I forgot to include it, so thank you for asking. And then we are getting to the end, so you need a front end that you put on the telescope. So that thing is the front end, which you put on the telescope, and then this houses the thin fibers on the inside. So here you can see the central box of that open, and this is that little mask which will obscure every other fiber and some other things it can do. And then this is the little unit which has the plug plate, and this was the prototype, so it only had 200 fibers. But you can see the box was designed for 2,400 fibers. And so that little part there in the middle, that contains not a full bundle. So this is the completed bundle of 2,400 fibers. And then this is the fiber management of the 2400 fibers, as it goes into 8 shelves and then to the 8 slits. And this is the finished array seen under a microscope, and this is a zoomed in version of all the clean fiber faces. But you can see here, this is green and this is not green. It's because we had to, of course, put anti-reflection coating on those tiny fiber ends. So what we did is we, again, had a whole thing. We had special fixtures, and we packaged all the fibers because they have to go into a vacuum chamber for that. So they were all spooled up, and we built little boxes which hold all the fibers with their just end faces protruding out of that very carefully, and then they put those into vacuum chambers. But of course, all this fixturing was so big, we had to do 4 runs of anti-reflection coatings. This was the first run, this is the second run, this is the third run, that was the 4th run. So something happened to the vacuum chamber, so some contamination shifted the anti-reflection properties. It's still good, it's just a different coloration. Just like in your lenses, sometimes you have, bluish or greenish or reddish hue, and you can see that was a different batch. And so this is, just as I was coming out of the lab, I'm like, okay, I'm gonna snap 2 pictures. So this is one of the pictures. So we are entering the first bench. So where we are today, we have all the cameras, the optics assembled, all 24 of them, and metrology has been done on most of them. And then we have all 4 carbon fiber benches built up on both sides with all of those cradles and all of the other pieces. Metrology was done on them with a CMM arm. So everything has been positioned to essentially a mill on the bench, and now we are just inserting the optical elements into it. And then we're double checking the metrology with a CMM arm to make sure that we're really where we are. And so here you can see the red camera is not in that, but the blue camera and the green camera is in there. You can see that this is a test fiber assembly. It's not the real fibers. It just has a set of fibers to illuminate the whole thing and test it. And so that's where we are today. So the first bench is going to get integrated maybe next week and see first light. And then we could immediately, it's on a rotating thing, so we can just flip it on the other side and build up the next one. And then we put it aside and then do it 3 more times over. What's missing yet, because I lost one of my engineers, that's why you're hiring, hopefully. And there's this whole frame structure that actually brings this onto the telescope. Because on the telescope, we couldn't use one of the Naismith platforms, which would have been beautiful and simple, but this telescope is heavily used. Magellan is one of the best performing telescopes out there. It has lots of instruments. So we had to go to something called a folded Cassegrain port, which is on the side. And so as the telescope moves, this kind of swings in the air. But all these fibers and all these things are so sensitive, we don't want to have it see changing gravitational environment. The design would have been much more complicated. So what we're doing is we are pivoting it. And as the telescope goes down, essentially this just swings. And so gravity always stays in the plane of the bench. You can see that the one of those units blown up there is shown here. So the optical bench is vertical and it's symmetrically loaded on both sides. And so there's no bending moment and nothing. And this always points down, even when the telescope goes. And what we are missing is these unit frames are being manufactured now. And then this had to get a little bit redesigned for certain reasons. So that's the component that is still being made. And then once these unit frames come back from anodizing, we can assemble them, and the first spectrograph is probably ready by then. So we put it in, and then these have little rollers, so we can roll in the corner, and then build 4 of them. We all test, and then we bolt them together for final test, and then disassemble them and ship them, hopefully, into Chile very soon. And so that's where we are. And then I'm going to stop there. Well, it's a little later, but thank you for the attention. And then I just wanted to say that, yeah, we might work with 6.5 inch telescopes, but it's not the size of the telescope that matters. It's a wonderful world out there, and you can connect it with it whichever way you want, and it's all good. But if you want to connect it through some of those and you want to come and work, we are hiring. If somebody wants to do some cool stuff, then we'll have some openings very soon. And yeah, thanks for the attention. Questions?
That final assembly is swinging, as you say, every time the scope moves. Is that going to increase stress on the fibers?
No. So the fibers, so it's an all-azimuth telescope. So this thing has to rotate because the telescope tracks in 3 axes. And the fiber bundle comes out, and then they are fed into these, but there's a loop of fibers. And so that can take up the torsion from the rotation and then from the swinging motion. And they are in essentially steel braided conduits. So they enforce a minimum bending radius so the fibers are not stressed at all. So there's a fiber management system going with it.
So 2,400 fibers, and it's feeding 8 sets of 3 camera sets.
Yep.
So is it sort of like a 45, 48-ish by 38-ish away, the 2,400?
Yeah, yeah.
Okay. And therefore it's 300 in a straight line feeding each column here?
Yes.
Okay.
Yep. Yeah, and so it covers 36 by 36 arc seconds on the sky. So essentially size of Jupiter-ish with an angular resolution of 0.7 arc second per fiber, because the median seeing condition on Las Campanas in Chile is 0.7. So it's a natural seeing instrument.
Any plans for it?
No, because so this one was 7 million. That was hard to get, and then if we would do a bigger one, we would do it probably differently a little bit. But yeah, so not a plan for a bigger one. So other instruments. So a lot of questions. I don't know who was who. So let's go this way. Corey.
Did the vendor that made the microlens, did they reveal how they do it?
Yes, it's kind of a known thing. So it's a similar thing how integrated circuits chips are manufactured. So photolithography. No, it's essentially they use masks and they put a photoresist on the glass, and then layer by layer they build the negative of the lens, and then because it's multiple masks, it would be like a ragged edge. But then what they did, and that's why those microlens are really super smooth, is that they very gently heated up the multi-layer photoresist in the shape, and so surface tension just pulled it very, very smooth, and then they etched it. And so this way it was very super smooth. Very nice. Yeah.
As the instrument is actually used, is there either a procedure or are there sensors on the system that will tell the user that it's still in tolerance? I mean, how do you know if things go wrong in this device?
Yeah, so we take calibration images. We have arc lamps that gives essentially an emission spectrum across. And so we can use that to check focus, make sure that everything is in focus, and then make sure that nothing moves spatially. But again, because there's no change in gravity, and then the basic optical bench that registers each component to each other, that's carbon fibers with almost 0 CTE, it's not expected to change. And then in the lab, we test it, and everything seems to be fine. We have focus mechanisms, so we can continuously change focus. If there would be a temperature-dependent focus component, we could just tie it to an automated loop. But many of these details we'll have to see once it's in operation.
There's pretty tight temperature control on the spectrograph.
So there's no temperature control. It was designed not to need it because it's in open air. And then in the dome of the telescope, you cannot put more than I think per instrument 75 watts into the dome air. Now, each of these cameras, because they're thermoelectric cooled, I showed you that Muse system, which looked like one of those Matrix robots there, and that instrument is liquid nitrogen cooled. So a lot of that piping is liquid nitrogen, but that's really complicated. So we wanted to not do that, and we decided to use thermoelectric cooling. But thermoelectric cooling is very power hungry. So we have a 5-stage tech in order to push the CCDs down to -90 C. So we provide 10 plus 10 C water glycol mix in the back. So what you don't see, but there's a whole piping system, but it's glycol. And that's not a reason why the spectrograph is facing down and gravity, we want it that way, because all the cameras and the piping is in the back, and it's always gravity loaded. So if there's ever a leak and there are splash guards inside, it only goes down, not into the optics. And a 5-stage tach is about 100 watts. So with everything thin, it's like 3 kilowatts in there. So we're pulling 3 kilowatts out. So it's a really big chiller and a really high flow rate to do that, not to put anything into the dome.
Very nice.
Maybe you have this on one of your charts. What was your ultimate R, your spectral resolution?
2000.
2000.
Yes. Yeah. So from 3,500 angstroms to 9,750 angstrom, which is about 6,000 angstroms, we have 6,000 pixels, but we are also sampling each spectral line with about 3 pixels. So we have 2,000 elements of the spectrum. And if you work out the math, it works out to be also 2,000 resolution.
Is your presentation available online? I know there's people I'd love to show to.
I can make it available online. And the only thing which was in there is the.
You can't really get the guy's sound.
And just get that like 12 minutes.
And as I said, I'm happy to have a couple of smaller groups in the lab to go through. We have to arrange that, but we can do that. You can see the thing.
Spectacular.
Yeah, very cool.
Yeah, excellent.
Good, well, thanks again.
Yeah.
And if you're looking at
Okay, so with that, we'll officially end the meeting.
Just make sure
Next
the
meeting
business
is
doesn't
January
get into your
12th.
eye.
So it's only partially populated.